So far, we've looked at two different ways to organize living organisms with their ecosystem. One is called a trophic ladder, and trophic means energy, and that's how we organize how energy moves from one level to the next. And as we'll discover, a lot of energy is lost as you go from one level to the next level. And we saw how we can have producers who basically get energy from the sun and then convert it to chemical energy, and how that's passed on to various consumers, and then how eventually it's processed by decomposers, detrivores, or saprotrophs at the end, who, while they take all the energy, they certainly cannot put that energy back into the soil, but they can take the nutrients back into the soil. So trophic means movement of energy, but oftentimes it shows the movement of nutrients. And another way we saw to organize this was to go ahead and take a single trophic ladder, which we call a food chain, and to put a whole bunch of them together to create something far more complicated, which is a food web. And the more complicated the food web, that tells us the more stable that ecosystem is. And so hopefully in the exercise that we did, we saw that the rainforest food web was quite complicated, which means that if one of the strings is cut there, the web still holds together because organisms have other sources that they can rely on. We're going to talk about a third way today, which is called ecological pyramids. This is another way to organize information here. And sometimes they do look like a typical pyramid like this, sometimes they don't. And unfortunately, there's three different ways we could put them together. They rely on the variables energy, which we've talked about already, trophic. So things must move from high energy to low energy. And then there's biomass, and there's numbers, and I'll show you how these take place. Okay, let's see how they work. Well, first of all, you can see that a typical pyramid does not really look like a pyramid. It actually looks kind of like this, right? Ooh, like that. So it starts off really flat, and then it gets thin very, very quickly. And this should look familiar to you. So they're organized by energy. So we said that trophic is at the bottom, then your primary consumer, secondary consumer, tertiary consumer, and quaternary. So decomposers are not going to be put into this picture here. And the units is kind of funny. Units are something called kilojoules. Kilojoules. Now, joules is a unit of energy you should have been introduced to in chemistry. Per meter squared per year. So actually, if I was to write that, kilojoules would be on the numerator on the top, and then meter square down below here in the denominator, times year, like that. What does that basically mean? Kilojoules is the amount of energy. Meter square means in what area. So obviously, the bigger the area, you're going to have more energy. And then how much energy is being moved there in a time, and the time we use is per year. Let me say it again. All ecological pyramids must be organized by trophic, that is energy, starting with producers and moving on up, just like we've always had it done. Okay, now why did the pyramid get so narrow so fast? The 10% rule. In general, it's not exact, but in general, every time you go up level, you only pass on 10% of the energy, or you lose 90%. Wow. I mean, that's an enormous loss. So if you look back here, if we had 100% of the energy down here, right, in the producer level, by the time we got up here, there'd only be 10%, there'd only be 10% from that, or 1% from the original, and so on like that. So, wow, we really lose it fast. Now, why is that? Well, some organisms die before they get to pass on their energy. I mean, that's going to happen. Some organisms, or parts of the organisms, are not edible. So if a crocodile, for example, eats a deer, it can eat the meat and so forth, but it probably doesn't process the bones and the hoofs and all that sort of stuff. So some parts are not edible, some are not digestible. And that happens for us. So when we eat cereal, for example, a lot of it is bran, And bran is not digestible. Cellulose is not digestible. It flows through us, right? So we never extract the energy from it. And, of course, cellular respiration, while being very efficient, I think we said it was like 40% efficient or something like that. It's not 100% efficient. So even if we eat food, we lose a lot of the energy from it. 10% rule in general. When you go from one level to the next, you only pass on 10% of the energy. Okay, so a pyramid has to be organized by energy. So here we go, producers, then herbivores, then primary carnivores, then top carnivores. So they're just like we always did the trophic ladders. Now this one in particular will be organized on a second variable, which is biomass. So if you take all of those guys within that area, see down here we have meters squared. If you take all of that biomass, how would it be organized? Well, let's take a look here. The producers have a lot of energy, but they also have a lot of biomass, right? And then these herbivores, the deers and the bunnies, if you weigh them, have less biomass, and then less into the, I think that's probably, what is that, some sort of wolf or coyote? And then the lion at the top has the least amount of biomass, right? Now in this case, it went about 10%. It didn't have to be 10%, but that's kind of a nice average number. And the units of biomass, now this is important, have to be dry. We got to take out the water, and they're kilograms per meter squared. Okay? So this is what a typical biomass ecological pyramid would look like. Is this type of pyramid possible? Now here we got a pyramid, but wow, it's kind of upside down. Well, first of all, does it obey our agreement on trophic levels? Sure it does. Producers at the bottom, then herbivores, then carnivores. Now, if you weigh all of these guys down here at the bottom, surprisingly, they don't weigh that much. Now, in this case, the sharks and stuff at the top there actually weigh a lot more than the guys down here. Let me say it again. We're still only passing 10% of energy as we go from here to here, and only passing 10% of energy over here to here, but the biomass of the sharks is much bigger than the biomass of the producers at the bottom. How could that be possible? Okay, this is a level 3 kind of question. We got to kind of think about the biology here. Here is one possible explanation. Now, it doesn't mean that a small number of organisms don't add up to much biomass, but suppose that they don't live very long, right? Or suppose they reproduce really quickly. Okay? So let's go back here again. There's not that many of these guys here, but they reproduce really quickly. They die, they reproduce, they die, they reproduce. As soon as they get eaten by the fish, they just keep reproducing. So one of the explanations is the reason why there aren't a lot of them, a lot of biomass there, is that they reproduce really quickly. Okay? Or another explanation is that there's very few of them, but they just live really a long, long time, right? Okay. So the fish are eating a small number of plants, but the ones that aren't eaten just keep reproducing. So the biomass doesn't add up very much, but they still can provide a lot of energy and food. And that's a real kind of biology answer. Okay. The other way we can go ahead and organize an ecological pyramid is by numbers. You simply count how many are in that meter squared area. Now, once again, is this organized by trophic energy? Let's take a look. Shrimp are at the bottom. There's your herbivores. Then these are probably some sort of omnivores here. And then I think a pike is definitely a carnivorous fish. And then you got here an osprey. Is actually a type of like sea eagle. So that's at the top of the pyramid. Let's count them. 10,000, 1,100. I wish it wasn't always these nice even things of 10. It didn't have to be 10. But it sure looks like you have less and less and less of them as you go along. Okay. So in other words, it's very interesting. In order to maintain one eagle, one osprey, wow, you had to have 10,000 shrimp down there at the bottom of the ecological pyramid. Okay, that one's easy to explain, right? How about this one? Wow, this is weird. It's kind of inverted down here, isn't it? And then over here, it looks like the typical pyramid. How could we explain that? Well, first of all, does this obey the rule of a trophic ladder? So let's go ahead and see. We need to start with our producers at the bottom. Sure, we got our tree. Then we got birds who are herbivores. And then you got some sort of hawk or eagle at the top who's a carnivore. So energy is moving this way, and we assume it's following the 10% rule. Only 10% of the energy goes from here to here, right? Then only 10% of this energy goes from here to here. Fair enough, right? Now, how can we explain this? Now, this is based on numbers, right? Here's 1. Here's what do we got? 1, 2, 3, 4, 5. There's 6 here. That's why it's wider over here. And this guy is also 1. That's why it gets thinned out. Now, that's interesting, though. Why does it look like that? I mean, why doesn't it just look like this? Why are there so few trees at the bottom? And the answer, of course, is, hey, it's a really big tree, right? So the biomass of that tree is really, really large. It provides a lot of fruit and leaves for a small number of birds at the top. And those birds then provide food for the one big hawk. So the answer to the question was, it's simply a really big tree. Okay, not complicated, but you got to think about it a little bit. Hey, what if it's completely inverted like this, right? Does this make sense? Well, once again, let's take a look and see, does it obey the energy, producers, herbivores, parasites? Ooh, that's interesting. Parasites and hyperparasites. Wow, that's really interesting. But little things could be carnivores too, right? Energy passes in the correct way, and we assume it goes 10%, 10%. Now, this is a numbers tree, so let's count up the numbers here. We got one big tree, 1, 2, 3, 4, 5 of them. 1, 2, 3, 4, 5, 6 of them, and then, I don't think they put it in here, but let's just say there's a lot. That's the way it is. Well, once again, the tree is really, really big, right? So one big tree could provide these herbivores like that. How do we explain the rest of the pyramid? In this case, the carnivores, or those secondary consumers at the top, they're just really, really small. And that's why if they're really small, so these guys over here and these guys over here, they're really, really small, but there's just a lot of them, right? And that's why the numbers-wise, they look like this, but there's just a lot of them, so they can, all together, eat all the guys at the bottom. So there's just a lot of them.